Yes, now it's recording. So starting Medusa, then one goes to File and Data File and New and Create. Now I have pressed it, so then the hydrochemical database program called Hydra actually starts. And in order to compute a Porbet diagram, you select an element, say manganese, for example. Only one item is necessary because we select either manganese 2+ or manganese 3+. Doesn't matter actually which one you select. In addition, we select electrons. Those are given here as an extra element. I don't know why, otherwise there must have been an option to search for all redox couples also. So now we have H+, electrons, and manganese as possible components, and then all compounds that could be formed by these three components and water also. Adding or subtracting them, we shall see how many complexes are available in the database. It's quite a lot. It's H2, for example. I don't know what is the difference between H2 and H2 gas. Down here, here in this box below here, I need to stay with the mouse cursor. You see 2H+ in this area of the screen. 2H+ plus 2 electron is H2 gas. Log K is 0. So this is probably 2H+, forming the compound H2 gas from aqueous H+. Let's see, what is H2 then? Then it's 2H+ plus 2 electrons forming H2. Log K is 3.15. There need to be something different. It's not standard hydrogen ions in solution, or it's not hydrogen gas, but how was hydrogen gas? That's H2. Yeah, I guess it's hydrogen ions in gas phase. I can't come up with anything else actually, because hydrogen ions in aqueous phase should be a little bit more stable than hydrogen ions in gas phase. In gas phase, and when they find electrons, they should be very, very eager, which is reasonable then to have a large equilibrium constant. Well, there are a lot of elements, there are a lot of compounds, complexes, Medusa called them, and manganese compounds here, and oxygen, and still more manganese. So let's save these, save and exit, and then Medusa suggests to make a diagram. We should save them in a file, for example, with the name manganese. The extension will be .dat. And then it remembered now, the program remembered where I were storing my files from yesterday. Users Lars, that's my home directory, Dropbox, kurser, avancerad organisk kemi, Medusa, manganese.dat. Let's use that as to make a diagram. Now you can choose from the diagram type. You don't see pore bear, or because it's the top one which is not shown. You need to literally select it. Predominance area is equivalent to pore bear diagram. We can go to pH between 0 and 14. 200 calculation steps, that's reasonable. This box predom 2 is they have incorporated 2 different calculation program for the pore bear. Usually predom 2 is slightly better or faster. You can allow only aqueous species, but otherwise there could be solid phases also present. But we can. Here it says that PE should be varied. Since we haven't been speaking about PE, there is perhaps reason to check this box down here. Use redox potential instead. Then you see that what previously was between plus 17 and minus 17 now goes to from +1 to -1 approximately. Otherwise, there is no difference. We can maybe take it a little bit further down to -2 volts. Now I managed to get in 2 minus signs, and from 2 volt plus also. This is a very, very large area in the Y direction. But we'll see what happened. Make a diagram. And here it says that this will take a very long time. And the truthness of that statement is, it's more true today than yesterday. But still, it's not very time consuming. It will count up to 200 here. So here you see the pore bear diagram. For manganese, for the total concentration of 10 millimolars, this lower dashed line, green dashed line, is the hydrogen line, and the upper one is the oxygen line. We can see if I can annotate here. Yes. So essentially, here we should have H2 gas evolution, while from a hydrogen point of view, water is stable within the box. And up here above the oxygen line, we should have an oxygen gas evolution. This is perhaps a problem if you have a permanganate solution. You see that the existence area for the permanganate ion, according to Medusa, is above the oxygen line. So in principle, it's not stable in water. It will decompose to manganese oxide. Manganese oxide, MnO2, is stable, at least partly. It has a part of the existence area inside the box here. While manganese 2 plus is definitely stable, at least in acid and neutral environments. Here are a lot of solid phases. Down here you see the manganese metal. CR stands for crystalline, I think. And it is in the order of is it minus 1.3 volts or something like that. which is an indication of quite a reactive metal, much more reactive than the neighbors. The neighbors are, is it chromium and iron? Chromium is considerably higher up, and iron also. Why this manganese metal is so reactive? That could perhaps be due to the fact that manganese 2+ in aqueous environment is more or less stable. So what to do? Yeah, we close this one, and yeah, then you can in principle compare with other diagram and see if you have a common existence area. Otherwise, there are possibilities for the two different compounds to react, and you can predict and also what kind of product that is should be formed. We can make one more. No, file, new, create this one. I want to look at iodine, and then selecting one of the iodine species and electrons, and then search complexes, save and exit, make diagram, save the data in a file, maybe. Now the file is saved, so we zero, and we want to select the correct type here, move up to predominance area, and we want to use redox potential, and now I set -1 and 1.5. These limits in redox potential will fit nicely the water box inside it, but it won't make the water box especially, it will fill up most of the space. The basis of this program is actually some programs by Gunnar Eriksson from Umeå. He's not related to me, but Eriksson is quite common name in Sweden. He wrote something called Solgas water, and which is one of the famous programs. Here you see the iodine system and the so-called water box. You see that iodide ions, they are stable in most of the box, but also iodine, for example. Now one can maybe, now let's see, annotate, resume share. So annotate what happens if you have iodine and oh, this is difficult to. If you have iodine in a basic alkaline solution, what happens? So you are somewhere in that area, make it alkaline. It's no problem to increase pH even more, but where do you go? You can go to that point, and then you're forced to be on this equilibrium line. I mean, you can't go here because that is an oxidation. Why? What is your oxidation agent. If you add an external oxidation agent, then you may move vertically up. Or if you add a reducing agent, then you may move downwards. But you haven't. If you just hydroxide ions is not a good neither. Why isn't my pen working? Hydroxide. Oh, maybe I'm pressing some button. Hydroxide ions, they are only basic. But you see here, if we go from this iodine area, and if we stay then here on the border between the two other components, we can claim that this is a way to predict what will happen. So what will happen is that iodide and this was not easy. Now let's see. I'm too fast with this pen. That's why it doesn't work. Iodide and iodate. This is literally what is formed, but in what? So we can say that one of the reactions are with iodide, 2 iodide. Then let us balance this reaction. We can do that by taking 2 iodide ions. Then it's balanced except the charge. This is the reduction. And then we take the oxidation. Sorry. So, and one more. Iodide to iodate. So we should have basic, so we can take 2 iodide to balance the iodine, and then we have 6 what's it called, hydroxide ions, 6 hydroxide ions. Now iodine and oxygen is balanced, but not hydrogen. Hydrogen could be balanced most easily with the hydrogen ions. Let's see if I can draw with my finger instead. So 6, that was easier. 6 H plus. H plus and OH minus simultaneously is not a good combination. So then we add 6 OH minus and 6 OH minus more to each of the sites. These two will create 6 water. So now all atoms are balanced except the charge. 2 negative charge on this side, and 6 plus 6 is 12. on that side, so we need 10 electrons. See if I can tidy this one up a little bit. Oh, what that one? So, and let us tidy that one also. And replace this. You have 12 here. I think this the important thing is that now you see that 2 electrons and 10 electrons need to be scaled to each other. So then we multiply this by 5 and then it's ready. So you will get something like 5 and then you would have 12 hydroxides, these 3 of those, and no, 5, 6, I mean. 2 times 5 is not 5, it's 10. 10I minus, and 2 of those, and 12 OH minus, and plus 6 H2O. So you see that one can actually remove a factor of 2, so it's at the moment we transform this into a pad. Yes. So it's 3I2 plus 6OH minus goes to 5I minus plus IO3 plus 3H2O. This is the simplest version. And this is actually what will happen when we see this stay. Close that. When we go from the iodine area out on the border here between the iodate and iodide. So this is a disproportionation, and the use of the Pourbaix diagram is essentially to indicate that what is formed, whether it is it's iodide and iodide ions. Sorry for the mess here. No. Yes. So, that was essentially what I was planning to show for you regarding Medusa. Maybe we should stop this recording.